I changed a little bit the title of my talk, but still I will be talking about the same topics, so don't worry about that. Okay, so in this famous book, Major Transitions, I have to be here, Major Transitions in Evolution, John Maynard Smith, I never know how to pronounce that name, studied the different steps through the evolution that changed, that introduced really revolutions, that really changed how things were operating. And all these revolutions had some common traits. And the first one, the main one, the crucial one for us, is that smaller entities come about together to form larger entities. As in this example here, you have unicellular organisms, then they cluster together to do a colony, and at some point they become a multicellular organism. So this happens a lot of times through evolution, and this is the clearest example that more is different, and that maybe sometimes more is better to progress and to go ahead. And within this setting, I want to pick up the best example. So as written there, the best illustration that more is different and maybe is better many times, I'm going to talk about the human brain. This is the first time in the human history that the human brain is mentioned. It was these years before Christ, and if you have some patience, you can find that in this papyrus from Egyptian times, which is talking about headaches and epilepsy and something like that, it seems. Okay, so in this talk, I will be talking about a few aspects of the brain. And when I mentioned to my daughter, she's 11 years old, that I was giving this talk in Paris, and I was kind of nervous and very busy preparing it, she asked me, so Dad, who is the hero of your story? I said, the hero of my story? Then I realized I needed some heroes to tell my story, and that could be much nicer. So I want to talk about these three aspects: the structure of the brain, the dynamics of the brain, and the function of the brain. And for that, I selected my three heroes. Here, is this working? Okay. These three people that I will introduce to you now in what follows. Okay, so start with structure. So for the structure, I pick up the Spanish scientist, one of the few Spaniards with the Nobel Prize in Sciences, I'm sorry to say. And Santiago Ramón y Cajal, he was the very first that, observing in the microscope tissue from the brain, was able to identify that neurons had their own identity, so that they were individual cells, like in the rest of the body. And that was against the accepted theory that viewed the nervous system as a continuous. But after him, we know that it's individual units that talk together. He was also the very first one to see the synaptic buttons, so the way, the points the neurons have to communicate with each other. Okay, of course, nowadays, this is one of his marvelous paintings. There are 2,000 of these in the museum in Madrid. So nowadays we know that of these objects we have 10 to the 11, and the connections between them is 10 to the 15. So these form an extraordinarily complex network object that, as some people say, the human brain is the most complex object known to the human brain. Right? So, okay, but since the times of Ramón y Cajal, technology has improved, and this is a big thing. So, for example, this is one of his drawing of a Purkinje cell, and this is a picture, a photograph done with some modern technology, two-photon imaging. And so this is a small scale, the neuron, and this is a larger scale. We have this Human Connectome project where they mapped all the large-scale connections between different areas of the brain. Okay, so all across my talk, I will be talking about two different two views of the same universe: microscopic, macroscopic. Okay, keep that in mind. Keep that in your brain. So with this type of data, you construct these things. You have a reconstruction of parcellation of the brain, so you know which part is connected with which part, and from this network you can construct a matrix. And this slide is too technical, but I just have to add it to illustrate that the network here is very hierarchical. It's like a fractal. You have moduli within moduli. And I also have to put this because of Jean-Philippe. He organized this nice conference, so I have to say something about random matrix theory, and I will be talking about spectra of matrices along my talk. So, for example, this is the spectrum of these matrices of the large scale thing, and they are not random matrices. They don't obey separate circle law. They have these beautiful tails here, which is, if you look at this matrix, is what in physics we call a Lifshitz tail, which is something well known for disorder systems. Whatever, that's a technical thing. Okay, so dynamics. For the dynamics, I chose my hero, and he's Hans Berger, almost Berger.
The spectrum you showed us was for large scale.
Yeah, large scale. That's where good data are. Yeah. Okay, so this is Hans Berger, and almost 100 years ago, we should organize a meeting in 2 years from now to celebrate. He was the first one measuring the electroencephalogram of this young lady, and he was the very first one to see these oscillations. And this is the first manifestation of collective effects in the brain. In order for us to see this out of the skull, you require thousands of neurons to do something together. So they fire together, so we can actually see that signal. And that signal is important for communication or whatever. Here, we have how things have improved in what regards dynamics. Now, with these technologies, we can see with our own eyes, with the microscope, when the neurons are firing. So they get green, flashy green when they do so. And we can measure the activity at different scales. And for example, now they have this technology, neuropixels, in which they have a proof, not in the human brain, but in the rats, on the mouse, and they can record tens of thousands of neurons at the same time, every single spike, okay? So that's really amazing. And the movie you could see here, it's by my collaborators in Japan. It's an artificial neural network in which they are creating something that looks like brain, and we can record, of course, the activity. I will come back to this at the end of the talk. Okay, so what about the dynamics at the large scale? So the large scale, we have this technology, functional magnetic resonance imaging, fMRI, in which you can record this type of time series across the surface of the brain, and you see that some of them are correlated, some of them are anti-correlated. So again, you can construct some metrics, some correlation metrics that has some interesting structure, okay? And we would like to understand that. This is a movie that one of my students did using data from the Human Connectome project. So we have this type of time series, and here what I am illustrating is that I am projecting them into the main modes of vibration, if you want, of this network. So essentially, we take the network, we construct the Laplacian matrix, and these are the eigenvectors, the eigenmodes of the Laplacian matrix. So you see that they are getting switching on and off in this spontaneous state of activity. Actually, if we project, something went wrong, sorry. Hello? It's just slow. Okay, if we project in the whole spectrum, this is the log of the eigenvector, you see that the power is very variable. Actually, it's a power law, you can see there. Okay, here is the power law of the correlation matrix. So the regions are correlated in a way so that you take the covariance matrix, you diagonalize it, you look at the eigenvalues to do principal component analysis, for example, and you see that you have a bunch of them. You have many of them that are nested in a whole hierarchy of modes. So it's resembles very much what we statistical physicists like about critical points. This is the famous Ising model. And if you're sitting right at the critical point where you change from being disorder, like here, to order, where one of the magnetizations dominates, if you are right here at the transition point, you see these beautiful things, and you have all the things that we saw this morning in the talk of Andrea Cavagna, the wonderful talk by Andrea Cavagna. Okay, so this type of very rich structure. And only if you sit there, I'm going to do it here, you see this type of a spectrum of covariance matrices, right? So this, at least for statistical physicists, maybe there is something that could be similar to critical point in brain activity. I don't know. So third aspect is function. What I'm going to say about function, okay, I pick up my hero, and my hero is Alan Turing. So he wrote in 1950, this thing. It's a little bit longish to read, so I'll make a summary for you. Essentially what he says is that he wants to construct a machine that works in such a way that if you inject an idea, the idea should be this thing here, then it doesn't fade away. It can, on the other hand, create an avalanche of other ideas, subsequent ideas. So here you are extremely creative, maybe schizophrenic, I don't know, but should be something ideal in between, where ideas can generate a cascade of other ideas before extinguishing. And he wanted to understand if you could construct a machine like that that can think and generate new ideas. Of course, this was very metaphorical, but let me just spend 1 minute telling you this simple model is very simple, but I will use it. So imagine you have some active site in a network. For example, you can think of this of a meme in the network of WhatsApps, okay? And with some probability or some rate, you propagate it. With some other rate, you just delete it from your computer. And imagine this is a one-dimensional space. At the beginning of the time, this is time, this is space. Here you put your meme, and it propagates a little bit. It goes to some neighbors, but then it disappears from the world. On the other hand, here, it's so popular that it becomes viral, right? And if you are right in between, you can have this type of marginal propagation, and this is the critical point. And here you have a scaling variance and all the beautiful things we like about criticality. So you can generate avalanches of different sizes, and if your system is large enough, this becomes larger and larger and larger, and you can rescale things and make all these things collapse into a unique curve. So all this, of course, is very well explained by the theory that we learned this morning. Okay, but Alan Turing was very metaphorical in that paper. I don't think we have to take it very seriously. But he was very serious in other respects. And actually, he's retained the father of computer science and artificial intelligence, because essentially he defined what nowadays is called a Turing machine, which is a mathematical model of computation describing an abstract machine that manipulates symbols on a strip of tape according to the table of roots. So it's something like this. You have a sequence of zeros and ones, then you transform it to a new sequence, and with that you do computations, right? So the thing is that this was like mathematical abstraction of what computation is nowadays. That's why he's the father of this. So the thing is that despite the model's simplicity, it's just very simple rules to transform zeros in ones and ones in zeros. This thing is capable of implementing any computer algorithm that you can think of. It's Turing complete if you obey that. So question, under what condition will a physical system support the basic operations required for information transmission, storage, modification that requires that computation? So under which circumstances we can construct something which acts as a Turing machine? Okay, I go back to the 80s and I present you, I mean, maybe you all know these people. So let me focus first on Chris Langton, and he was working with cellular automata, which are very simple models in which you have zeros and ones and some rules to transform zeros and ones. Right? So he realizes in this family of cellular automata, you could end up in situations like this, where all the positions are zero, or you can have something periodic, or you can have something very, very chaotic, changing all time. So what he realizes is that in between this chaotic regime and this trivial fixed regime, there is an intermediate regime of this cellular automata, where you get something that we call complex. And he suggested that by working here, you can implement something which is a Turing machine, complete Turing machine. Actually, all these people here, including, of course, Stephen Wolfram, pushed a lot that type of idea, and that can be condensed in the name of computation at the edge of chaos. Only at the edge between trivial and chaotic, you can do intelligent things. And the logic a little bit, I want to give you the intuition why critical is good. In all the contexts I will talk about in this talk, criticality is a point in between two different things, an order and a disorder phase. And in this case, is good because it's not too robust, but it's not too noisy either. You want something in between flexibility and robustness. And this is a common thing that will appear again and again. Okay, so these very clever people implemented this in neural networks. So not just these things with zeros and ones, but they started to create more complicated networks. And if you measure the performance of these guys, you see that the top performance is in between the two phases, between when it's order and disorder. There are also field information theory approaches to this that I skip. Oh, I also skipped this one. Okay, so from these, there was more a whole idea of doing computation, which is called reservoir computing paradigm, that I think I skipped for the moment, but I will come back to the end to this possibility. Okay, so this is my introduction. The story of my three heroes is finished here. And now I ask, okay, so given all these antecedents, can we find something like this in the actual brain data? Okay, so I'm going to look for some experiments, and as a disclaimer, from now on, I will start mixing up structure, dynamics, and function much more than I have so far. Okay, so these are the experiments by Dietmar Plants. I hope they work. Okay, so back in 2003, 4, 7, I don't remember when, he was observing this tissue. It was in vitro, but then they made it in vivo. These are electrodes, and they are recording electrical activity in the neurons nearby this region. This is local field potentials, it's called. And what you see is that sometimes it's kind of silent, and then from time to time there is some avalanche of activity, some outburst, some whatever you want to call it. And they analyze the statistics of this, and they saw a power law that also obeys the scaling that I mentioned before in the simple trivial model I showed you before, right? So the sizes of these avalanches are scale-free. You have many different sizes, and they obey scaling. And this is the empirical data, and this is the model I showed you. So they resemble each other quite a lot, at least, I mean, even quantitatively, okay? If you want to see something more modern, these are avalanches of activity in the brain of the zebrafish. This is a good example because the zebrafish is transparent. So you can actually see with these modern technologies what every single neuron is doing. And you can see here this, if you put a threshold, you see avalanches. And these avalanches are big, large, small. So the distribution of sizes, again, is a power law. And now we have like 5 decays, which is not too bad, and also for time durations. Okay, if you measure the exponents of these decays, there is some dispersal, so it's not that it's really universal. The model I showed you should be here, and what people measure is something there. So, well, it's not that clean, but it's not too bad either, okay? So this triggered a lot of activity in people trying to understand this criticality hypothesis. So understanding if this data means that their brain is really working in something that resembles a critical point, and they started bringing up possible advantages. I already mentioned some, but for example, in these critical points, you have very large correlations, and that's very good to entail collective effects. And you have, I don't know, a lot of features, and for each feature, you can think of some possible advantage as reviewed in this paper here. So the view of the brain I told you so far is something like this. Is this picture that, to be honest with you, I don't like. Because this means that if the brain is really here, we are very close to be deaf, because this is deaf, and this is alive epileptic. So this is a little bit unsatisfactory to me. I don't really think we can be there. For earthquakes, it's okay to be off for a long time and then appear, but for a brain, I'm not satisfied with this, to be honest. So this also brought the idea, a revival of self-organized criticality, you know, in the famous sand pile of Perbach and collaborators. Without tuning anything, you have again these avalanches that are scale-free and they have power laws. So of course, people start thinking, well, the brain has to be self-organized critical. And these are 2 papers in Nature Physics, 2010, around 2010, claiming self-organized criticality in the brain. Okay, so for those of you not so familiar, it's self-organized criticality is a mechanism by which a system self-tunes itself to the critical point. You don't do anything, you don't have to be there, it just gets stuck there. So as I said before, I was not very satisfied with this picture, also because together with my dearest colleagues, Ron Dickman, Sandro Spignani, Saperi, 20 years ago, we had worked out the theory of self-organized criticality. Actually, we wrote down an equation very similar to the ones that Andrea Cavagna was discussing here, a model G or whatever, to understand all the features. And we understood that to get organized really to the critical point, you need the system to be conservative, to have separation of time scales, whatever, some ingredients that for sure are not present in the brain. You don't have separation of brain scales, of time scales. It's not that you do a perturbation, then you wait for the perturbation to relax, then after a while you have another, no. It's a continuous going on of things, and also there is no conservation, so I didn't believe these papers. So actually, I spent some time, this is how I entered the field. I entered the field by being curious about it, but also skeptical about what people were saying. So we reanalyzed these papers, and we conclude that this model, for example, this does not produce scale-free avalanches, it's not self-organized, and it doesn't even have a critical point. So it was all a mess. And with all my respect to the people that I appreciate a lot, and they're very, very good, but they didn't really know what self-organized criticality is. So actually, by looking at this model, we realized that rather than a critical point, what they have is a discontinuity. It's a first-order phase transition. And that inspired us to construct it. This was the original title of my talk, so I felt that I should include this slide here. My talk was Feedback Mechanism for Self-Organization to Edge of a Phase Transition. So this one is self-organized criticality. Essentially, you have a system like this that I presented to you before, and what you have is a mechanism by which, if you are active, you dissipate. Okay, it's like in the sand pile, when it's active, you dissipate in the boundaries. And if you are inactive, you charge, like in earthquakes. If you charge, at some point you reach that phase, you become active, you have an earthquake, you dissipate, and you come here. And this is this alternation between charging and dissipation at separate time scales that gets you to the critical point. But we realized that maybe, almost for sure, it's more interesting to study this type of discontinuous transitions in the brain, for reasons that I don't discuss now, but this is more relevant. So we invented new self-organized mechanisms for this type of transitions. We call it self-organized bistability. The acronym is not very inspiring. And also approximate mechanism in which you have imperfect organization. So at the end of the day, what I want to just to jump is that we decided that you need discontinuous transitions and imperfect organization because you don't have separation of time scales. And at the end of the day, what you generate in every region of the brain is oscillations. That's something that we knew before. So we put that in the model. We just modified the existing models, and this is the outcome. We have a phase in which neurons or regions in the brain have activity which is asynchronous, is very irregular, and a phase in which they fire synchronously. Okay, and in between you have a critical point. Okay, and this is this is the critical point I kind of believe in. So the brain is never off. The brain is somewhere in between asynchronous or synchronous. Actually, if you look data, they usually look real data of real neurons. They usually look like this. This is more asynchronous. This is more synchronous, and you see something with intermediate levels of activity. Also, at that critical point, we see avalanches, and we measure the exponents. So we wrote our paper saying that many features of the brain can be explained with a transition from asynchronous to synchronous. So it's like, okay, this is the Human Brain Project, this huge project in which they made a huge, amazing simulation of the brain with no parameters. All parameters were taken from experiments, the number of neurons, the synaptic connectivity. They put essentially a piece of brain into the computer. They did this, expend I don't know how many $1 billion, and the result is that the simulations further suggest that cortical activity in vivo approaches a critical transition along the synchronous, asynchronous spectrum between the other. Okay, so it's the same conclusion we reached. And what about large-scale synchronization? So I already mentioned this. This is the network of connections. These are the dynamics. So these are the network of correlations. And as physicists, we would like to solve this problem. We know the structure. we know the correlations, we want to have a model that does this. It's like in quantum mechanics. We want to know the excited states that can emerge from this type of structure. And actually, I come back to this picture I showed you before. We are exciting a lot of modes here, and we are measuring this I showed you before. So now we have our model, which is close to a critical point, a synchronization critical point, and we are able to reproduce all these features pretty nicely. Actually, this is just very briefly. Now we don't believe there is just one critical point. I think we think it's a region, something that in physics is called a Griffiths phase, separating synchronous from asynchronous regimes. So it's a little bit broad. It's not just a point. So it's a region, a transition between being synchronous and being asynchronous, right? So before closing this, let me mention that both synchronous states and asynchronous states are good for the brain. They both have functional advantages. For example, being synchronous in this region here is very good because you generate waves, and these waves can travel all the way to here. So you can put together different parts or integrate different aspects of your. Instead, asynchronous states in which neurons are firing very irregularly is what you essentially see when you study local computation in local circuits. So it makes perfect sense to me that the brain is there at the edge of both. Sometimes you're asynchronous to do computations, sometimes you are synchronous to send information somewhere else. Okay, but something is missing, and now we move again to the microscopic world. And I mentioned before that we have these experiments where we have tens of thousands of data from this guy here. It's not human brain anymore, but it's. And I have to mention this wonderful paper by Miguel A and his group, who is sitting here, where they did the renormalization group. I'm very happy that Andrea Cavagna, his wonderful talk this morning, because now I don't have to say more things about the renormalization group. But what Bill did was try to do some I shouldn't go away, some type of coarse graining with neurons. So you have the actual data of neurons, and you try to put them together in super neurons that compress the information of some of them. You do that based on correlation, so the most correlated ones you put together. Okay, there are a bunch of interesting technical details that, of course, I skip here, but the answer is that when you apply the RG, you see that the actual data are scale invariant. It's like they are sitting at one of these fixed points that Andrea discussed this morning. In particular, what they studied was the hippocampus, this particular region of the brain, and the activity there is scale invariant. For example, just for you to see what this scale invariance means, again, I chose to put this spectrum of the covariance matrix, so you see at different levels of renormalization, of coarse graining, you have always this power law, and you have the collapse, so you can put them together. So there is scaling. There is all the nice features that you usually see in critical points. That's nice.
That's the covariance of what?
Scale invariance of
Covariance matrix. Covariance of what?
the covariance of the activity in a block. So you have a time series of some activity. Okay. So together with my students, we decided, okay, if it's critical, let's see if it's universal in the sense that in different parts of the brain, it's the same, or if that's just specific for the hippocampus for some reason. So we went to take data from these different sources, and we analyzed 16 different regions in the brain of the mouse for which we have enough data to do all this sophisticated analysis that requires quite a large number of neurons. And in the 16 regions you see here, this is the same plot I put before, the spectrum of the covariance matrix. So essentially, is the one you use to do principal component analysis. If you want to see the modes, again, you always see this type of behavior in which you have nested nodes. It's not that you have a few components that are important and the rest you can cut out. You have a whole hierarchy of modes acting. So that's interesting. And the results are rather universal, rather robust, but there is some small variability. I marked here the minimum and the maximum, I think. Okay, so there is some dispersion. It's not exactly constant like in a critical point. Okay, but luckily, in the last 2 years, we have two wonderful papers by two groups of theoreticians. This one is a group of Moritz Elias, and this is Chaim John-Polinsky, in which they learn using techniques from disorder systems, spin glass theory, this thing that theoretical physicists Like, they discovered or invented, proposed a way to infer what's the actual state of the network, just measuring the covariances. So you measure the pairwise covariance between every possible pair of neurons. You have the distribution, so some of them are very correlated, some of them are anti-correlated. You have a distribution. And from this distribution, using this technique, you can infer how far is your system from instability, from a critical point. You can do that. So we did that for our 16 regions. And look at this is rather spectacular, I think. This is the edge of criticality, the edge of instability. So this one is 0.98, 97, the farthest away is 96. So within a few percent, 2-3%, 4-5%, all regions are close to this edge of instability. Okay, that's empirical finding. We didn't invent anything. We just measure using it, right? Furthermore, I just added this slide for Bialek because I mentioned it in lunchtime. So now we constructed a very simple model of linear units that are put together in a network, but we tune the connectivity of the network to be at the edge of chaos. So we change the spectral radius of the matrix if you want. So if the spectral radius is small, is far away from being unstable, you don't see scaling at all. Look, for example, at this one here. Okay, but on the other hand, this is the spectrum of the covariance matrix. As soon as you get close to the edge of criticality, to the edge of instability, you get rather good collapse here, and you get scaling, and the scaling is almost identical for different magnitudes that I didn't mention before, but it's almost identical to the one you measure with the renormalization group exponent. So the moral is that a simple model of neurons working near the edge of instability is able to reproduce these things. So the different regions I mentioned operate at different distances from criticality. Or if you want, in other words, they have different levels of recurrency. In other words, if you are far from criticality, the network is weakly coupled, let's say. So one neuron influences relatively little others. Okay, so then everything is dominated by direct connections. But as you increase this recurrence in the matrix, and you're becoming close to the edge of instability, there is a lot of recurrency. So the effect of a neuron and a neighbor then influences the third neuron and the fourth neuron and then comes back. So it's a lot of feedback, a lot of feedback in the network. And when that happens, you're close to unstable and you recover all the things, right? So let me just briefly, in the last 5 minutes or so, mention 3 different research lines that we are pursuing. I will focus on the first one for a couple of minutes, and the other ones I will be very, very brief. So essentially, just to give you the overview of what's ahead, my group, we want to see if these ideas can be implemented first in silico. That means that we want to do artificial neural networks that profit from being at the edge of instability to do something nice. Second, we want to construct chips, electronic chips, with neuromorphic computation, also exploiting this idea. And third, we want real neural networks grown in vivo that can do this. Okay, so the first one is this idea of reservoir computing that I mentioned already at the beginning of the talk, even if very briefly. And this is a nice paradigm in artificial intelligence. It's not the main one. It's not the dominant one in which is deep learning. You have different layers. In this one, it's different. Here, what you have is that here you have some inputs, and these inputs are going to send some information to the network. And the network is just a recurrent network, much as the one I just showed result for. And you can change the strength of the connections to make it more unstable or less unstable, right? And the funny thing about this is that you do not train the weights as you do in usual neural network models, deep learning, but you just train a readout. So this input gets here, it gets projected into some high-dimensional space, and then you train some readouts to infer something, right? So this is the general paradigm, and we implemented it with my student, PhD student Guillermo Morales. We said, okay, we are going to train one of these networks to distinguish, to classify these digits in this famous database. Okay, we did it with the scheme I presented you before, and the performance is here, so it's the blue points are the performance, and tells you that the best area is this greenish one. And the greenish one is right below this star here, and this star here is the edge of instability. Here is unstable, here is stable. So really the best performance is obtained when you're operating near the edge of chaos. But we found something even more interesting that I really like, which is this thing. This magenta curve is the exponent of the covariance matrix. So we look inside our reservoir, our network of neurons. We look at the covariances between the different units. We diagonalize and look at the spectrum of this thing. And the eigenvalue is very close to 1, but slightly larger than 1. Okay, in this area here is 1.1 or something like that. Good? And this is in perfect agreement with this fantastic paper by the group of Kenneth Harris that appeared in a Nature paper 2019, in which they observed empirically the activity of neurons in the brain of a mouse while he or she was watching some movies. And they concluded this thing. The bulk population activity was high dimensional. This means that the spectrum of the covariance matrix had a lot of eigenvalues, right? And correlations obeyed an unexpected power law. The end principal component variance scale at 1/n. In other words, they found that in order for information, codification, representation of the information in the network to be optimal, you have to have an exponent slightly larger than 1, right? They prove it also mathematically. It's something really amazing. To have a representation that makes sense, I don't know if I have the slide here. Yeah, this is from Harris' group. So if you want to represent in the activity of the neurons these two guys in a similar way, you need that this is a space of, let's say, the firing rates of the neurons. So a point of activity here is supposed to represent one of these guys. If you want these two guys to be represented together, you have some mathematical conditions on the smoothness of this manifold. And if you impose that, you need an exponent that is slightly larger than 1. That's proved, right? So our neural network at the edge of chaos spontaneously does that. It's representing the information with the right exponent predicted by these clever people. The next to last is this neuromorphic computation. So this is not my initiative, or not the initiative of my group, but we just joined a project at the University of Heidelberg and Göttingen, where they have been working these neuromorphic chips in which with electronic components, you are programming these guys to spike and communicate as neurons do, okay? So they had a version with just 32 neurons, and they wrote this Nature Physics paper saying that sometimes when you set it to the edge of instability, to criticality, you have some computational advantages, but not always. And now we are working on an extended version, trying to see in which cases it's really critical and you can exploit criticality. So this is work in progress, but it's very inspiring, at least to me. And my final point is this thing. So this is a collaboration with people in Japan, in Sendai. Hideaki Yamamoto is the first author of this. These guys are able to construct in vitro neural networks. So here you are seeing in real time the activity of these neurons. Each one comes from a stem cell, so they have been differentiated, put together in a petri dish, and forced to have some activity. What we are exploring here is that if you just put a bunch of these guys together, they form a network, they start firing together and start doing something. What they do is something very epileptic-like. It's like they fire all at the same time. So what we are doing is that we are constructing some topologies, some structures that look more like the brain. So for the time being, we have this modular thing with some communication between these moduli, okay? And we are adding another ingredient, which is some external driving that in the brain come from thalamus, whatever. So we are making progress towards having an activity of these neurons that really resembles what's going on in the brain. It's not epileptic brain, which is the thing that essentially they have so far, but we are working towards having more critical brains or synthetic brains at the edge of instability. And I think that if The summary is that operating near the edge of a phase transition seems like an excellent solution to perform robust computation collectively. I have found this idea very inspiring for a long time, and finally, after a lot of conceptual conceptualization of abstractions, now we have data and we can really explore this thing and make use of it in technological devices and in neural networks and synthetic networks. So thank you for the attention, especially given the time and the sleepiness around. And I have to thank, of course, my beloved collaborators. These are PhD students of mine or ex-PhD students of mine, and these are external collaborators. Without them, of course, I wouldn't have done any of this. So thank you.